One good application of vector valued functions is representing something's position, velocity, and acceleration, more like kind of real world motion type problems. So we saw that a vector valued function, when we saw how to sketch them, was really just a vector that pointed to every point along a curve. So you can kind of think about a vector valued function as pointing to the position as an object as time increases or as things move along. So in problems like this, we're going to say an object's position is given by r of t, which we've already defined as x of t, y of t. And if it's in 3 dimensions, of course, we would have a z of t here also. So you can think about this as giving the position of an object at any given time t. Now, of course, way back in Calc 1, we learned what velocity was. Velocity is just the rate of change of your position over time. So velocity would be r prime of t, which is just, as we've seen before, that's just the derivative of each component. So that right there will give you the velocity of the function at any given time. Now, I'm going to throw this in here because a lot of people get this confused. What is speed then? Well, velocity is a vector, which means it has a magnitude and a direction that you're going. Speed is just how fast you're going, just the magnitude of it. So the speed is just the magnitude of r prime of t, which of course is the square root of x prime of t squared y prime of t squared. So that will give you your speed, of course, just the magnitude of the velocity. And of course, acceleration. Acceleration is how fast your velocity is changing over time. So that's going to be the rate of change of the velocity, which is r prime, or the second derivative of the position, which is just, of course, r double prime, x double prime, and y double prime of t. And of course, if there was a z, you'd have the second derivative there. All right, so let's talk a little bit about an object in motion real quick. We have an object moving along a path here. Of course, every point on the path represents its position. Now, our velocity is a vector. How does a velocity vector show up on a curve? Well, velocity at every given point is the direction of motion at that point, which means it's always tangent to the curve at every single point. And this should make sense because in Calc 1, we use the first derivative to find the slope of the curve, the slope of the tangent line to the curve. So we know that it's got to be tangents there, exactly the same. Now, to represent this case, the magnitude of that would just be how long that vector is. So if you're looking at this and it has a whole bunch of velocity vectors on there, I don't know if I do a couple more on there. The length of the vector would tell you actually how fast it's going at that part. Now the acceleration is the second derivative. Now back in Calc 1, the second derivatives talk to us about concavity. You know, which way the graph was either concave down or concave up. It's a little bit different here because now we're talking about motion. The second derivative is talking about acceleration. Well, here's where we need to get just a little bit of physics in here. One of Newton's laws of motion says that an object in motion tends to stay in motion without being acted on by an external force. Basic idea is you go out in the middle of nowhere in space and you throw a ball. That ball is going to continue on that path forever at the exact velocity that you let go of it, unless it's acted on by some external force. Now remember, force, again from Newton, is mass times acceleration. Now in this formula, mass is generally a constant, which means a force is really defined by an acceleration. So to have any change in motion, there has to be an acceleration applied to that object. Now, the acceleration has to be in the direction of the new motion. So if you looked at a picture like this, let's take a look at this vector. So at this very instant that it's right here, and if this is the path it's going to travel, it has a velocity going that way, but it's going to turn this way, which means the acceleration vector has to be somewhere pointing in this direction. And it can be anywhere from back here, say somewhere over here, kind of. That's still in the downward direction, to downward somewhere. And it can even be a little bit wider than that. And it can fall anywhere in that spectrum. We don't know just from this, we'd have to find it to figure it out. Because depending on the length and the angle that it makes is how hard it's going to make this particle turn. Right? The closer it is to parallel, the less it's going to turn, right? So for this one, the acceleration vector would be pretty close to being parallel that way. Now it could be going the other way also. It could be slowing down the particle. But it's going to be really close. If something's turning a lot, then it's going to be much more perpendicular to the path that it's currently on. So your acceleration vector always is going to be into a curve, because that's the direction it has to be accelerating. All right, so if I gave you a position vector, let's say given the position vector, r of t is t cubed, and I said find velocity, speed, acceleration. It should be a very, very simple problem. So my velocity, which you may see some textbooks do something like this, call it v of t, which I'm going to adopt in our next problem anyway, so I'm going to go ahead and call it v of t. We know is going to be r prime of t. That's just going to be 1 3t squared. So your speed, which is the magnitude of the velocity, is going to be the square root of 1 plus 9t to the 4th. Your acceleration, which I'm going to call a of t, which of course you want to write it as b prime of t, or r double prime of t, right? Second derivative of our position, is just going to be the derivative of our velocity, which is 0 and 6t. So for whatever this thing's doing, it has no acceleration in the x direction. It's only accelerating in the y direction at this case. All right, so very, very easy to find. Now, since we're talking about position and acceleration and all these kind of things, the next logical thing to talk about, as far as an applied problem, is something called projectile motion. Now, the idea behind projectile motion is you have an object that's being launched somehow from an initial force that's given to it, and then that force disappears. So wherever it's at, the only thing that's going to be acting on it is any gravitational field that it happens to be with, and that's all we're going to assume. We're going to leave off things like wind resistance and other things that may come into play. Excuse me. All right, so if we have a projectile, let's go here and draw a horrible looking cannon. Let's assume that this thing, this cannon right here, is launching a cannonball that way. Now, when something's being launched, it's being given some initial velocity, which means it has a magnitude and a direction that it was launched at. We'll talk about that in just a second. But here, once it leaves the end of the cannon, the only force acting on it is gravity. And since gravity is in the y direction, we can actually start out this problem saying, once the problem starts, once it leaves the cannon or your arm or whatever the projectile leaves, we actually know what the acceleration vector is. Because the only thing accelerating that object is gravity. Now I'm going to put a g there, and not 9.8 or 32 or any other number you want to use for gravity, because it doesn't matter what gravitational field you're in. If you're on the moon, this will work exactly the same way. All right, so the idea here is we want to know where the object is at any given time, which means from our acceleration, can we actually find the position function? So basically what we're going to do, except for the speed step here, we're going to go backwards. So let's see what happens here. I know to get to the velocity, I'm going to integrate our acceleration vector, right? Because the acceleration is just the derivative of the velocity. So when I integrate this, our v of t will be the integral of 0 g dt. t. So my velocity vector should be, well, the integral of 0 is just a constant. I'll call that c1. And that would be gt plus c2. Okay, so there's our velocity function. Now, we've broken this up into an x piece and a y piece for our velocity. Now, we're going to assume that since we set this problem up and we launched our cannonball, or whatever it is, that we would be able to measure how fast it's going in an x direction, let's call that v sub x, and how fast it's moving in a y direction, let's call that v sub y. Which means at time equals 0, our velocity vector would be equal to the velocity in the x direction and the velocity in the y direction. Okay, so if that's true, I should be able to kind of figure out what these arbitrary constants are right here. So if I know v of 0, which would be c1 comma g times 0 plus c2, if I know that that has to be equal to v sub x, v sub y, well, just like we did before, this will be c1 comma c2 has to be equal to v sub x comma v sub y. All right, well, that's easy to see then. c1 is v sub x, c2 is v sub y. So now I have a complete velocity function that says my velocity is v sub x comma g sub t plus v sub y. Now remember, v sub x and v sub y are just constants, right? It's the amount of velocity it has moving in the x direction, the amount of velocity it has moving in the y direction. All right, now I have a complete velocity function, but what if I wanted to figure out my position? Remember, that's what we were going for here. Well, to get to our position function, our r of t, is just going to be the integral of that. So r of t will be the integral of v sub x comma gt plus v sub y dt. All right, I'm about to draw this picture again, but let me go ahead and get this out of here real quick. It's in my way. So my position function should be this. If I integrate this with respect to t, remember that's a constant, so that's v sub x t. This is going to be 1/2 gt squared plus v sub y t. Ooh, I forgot my constant. Everybody look. 1/2 gt squared plus v sub y t plus c2. Okay, so there's our position function, but again, we have some arbitrary constants here. But again, think about our position of our original launch. Now, most of these problems, when we set it up, just for convenience sake, this is where you're going to see most of them. Just for convenience sake, we almost always started at x equals 0, just to make our life a little bit easier. But you don't have to. But according to this, if we start this at x equals 0, then we would have some initial height. So I'm going to call that h, which means our position at time equals 0 was 0h. If it had some other initial position, like it was shifted left or right, that's what it would change here. So if I know r of 0 would be v sub x times 0 c1 1/2 g 0 squared plus v sub y times 0 plus c2 0 h. Okay, cleaning this up, again we end up with a very simple equation. C2 is equal to 0h, or c1 is equal to 0 and c2 is equal to h. So our final position function of a, well, almost final, position function, v sub xt plus 0, again, that could be shifted, 1/2 gt squared plus v sub y t plus h. Now this is getting very, very, very close to what you saw in pre-calculus when you had the height of a projectile. If we're only looking at the height of an object, This was the formula you were almost given in that class, except for most books called this V naught, where all the velocity was in the vertical direction. So we have to put a Y there. All right, this is really, really close to the ones that you're going to see in most textbooks. But this is given explicitly that we're given a V sub x and a V sub y. Most of the time, though, if you think about how things are launched, we know a magnitude and we know the angle that it was launched at. Right? We know it was launched at 500 feet per second at 45 degrees. So most of the time we're not given how much it's moving in the x direction and the y direction. So we're given the velocity here, the magnitude of the velocity, or the speed that it's coming out at, and an angle. Which means if you take a look at this triangle, I'm going to sketch it here, then I'm going to erase it. We end up with this. We have this side of the triangle, which we call the magnitude of V. We have this angle there, and I'm trying to find the velocity in the x direction and the velocity in the y direction. Now hopefully we've seen this problem enough to where we understand it. V sub x is going to be what? The magnitude times the cosine of the angle, and V sub y is going to be the magnitude times the sine of the angle. So the formula that you see most of the time for this is a little bit more complicated. V sub x is the magnitude of the velocity times the cosine of the angle, t, and 1/2 gt squared, magnitude of the velocity times the sine of the angle, t, plus whatever initial height it started at. All right, this is the position function of a projectile, as long as we're ignoring things like wind velocity and coefficients of friction and a few other things that we'd have to worry about. So you're gonna have to deal with a few problems in your homework where you're using this as a starting point to solve problems, like how far will a projectile go? Let me give you a few hints. These all turn out to be Calc 1 problems because they're gonna ask you things like, what's the maximum height of a projectile? Well, if you're talking about height, you're solely talking about the y component here. And to find minimums or maximums, you're taking derivatives. If you want to know how far something goes, well, you'd be talking about the x component then. So make sure that you're trying a few of those projectile motion problems because they are very real world issues, the type of problem that you might run into.